In this video, we'll discuss Marstrand's rectifiability criterion. So recall when we first introduced rectifiable sets, we gave the following characterization. So an HM measurable set, a finite HM measure, is M rectifiable if and only if at almost every point its tangent measures are all flat measures and the lower densities are positive. And this is equivalent to at almost every point there existing a single plane, V sub x, so all tangent measures are multiples of Hausdorff measure restricted to this plane, and the lower densities are positive. So we've already shown that rectifiability implies the tangent measures are all multiples of the same flat measure at almost every point. And in the same proof, we could have also proved that the lower densities were positive, but we'll in fact show something stronger in a later video, that in fact, for rectifiable sets, the densities are equal to 1 almost everywhere. What we're going to show in this video is 2 implies 1. So if at almost every point the tangent measures are all flat and the lower densities are positive, that implies rectifiability. So it would actually be easier for us to show 3 implies 1, just because this is a much stronger assumption. However, it will be useful for us later to be able to have this flexibility, to be able to deduce rectifiability just by knowing that all tangent measures at almost every point are just flat measures, even though a priori we don't know if there's a unique tangent measure at every point. So the implication that we'll prove today will actually be a consequence of a stronger theorem called Marstrand's rectifiability criterion. So Marstrand's rectifiability criterion states that if we have a radon measure mu, whose lower and upper m-dimensional densities are positive and finite almost everywhere, and the tangent measures at almost every point are m-dimensional flat measures, then the measure is rectifiable. So let's see how this proves the part of the previous theorem that we want to show. So suppose that we have a set A, an HM measurable set of finite m-dimensional measure, so that the lower densities of A are positive almost everywhere, and also that the tangent measures of Hausdorff measure restricted to the set A are all flat measures at almost every point. Okay, well, recall now that from our discussion of densities that when we have such a set A, that the upper densities are at most 1 almost everywhere. Okay, so that means that we can apply this theorem with mu equal to Hausdorff measure restricted to A, and then get that the measure HM restricted to A is rectifiable, and hence the set will be rectifiable. So we're only going to, in the notes and in this lecture, we're only going to focus on the one-dimensional case in the plane. So in other words, we're going to prove this theorem, we're going to prove this theorem for measures supported in the plane whose upper and lower one-dimensional densities are positive and finite, and the tangent measures at almost every point are multiples of Hausdorff measures restricted to lines through the origin. Now, the general case when n and m can be any integers is very similar to this proof. However, considering this case will just make some of the geometric arguments a little easier to explain and illustrate. Now, in this video, we're going to make an extra simplifying assumption that will make the proof a little bit different but easier to explain than what's in the notes. So recall that we had this lemma about alpha numbers. So suppose we had a radon measure mu, and we let EMR be the set of points so that the measure of any ball center x inside EM of radius s was trapped between m times s to the m and s to the m divided by m. So the measure of this ball is comparable to s with constant depending on big M, and that this holds for all s between 0 and r. Okay, so if we look at this set, then for all points x and y in this set, where y is close to x in the sense that it's inside the ball center x of radius r over 2, then by making alpha small enough, we can make the distance between this point y and the support of the best approximating affine measure as small as we wish. So let's say this is a point y inside that set EM. By picking delta small enough, we can make sure that this point y lies close to this plane. And then furthermore, we had this sort of the opposite direction. So for a point x inside EMR, and for all epsilon between 0 and r over 2, we can find the delta so that if the alpha number is very small, then the measure of any ball of radius epsilon r along this plane, LXR, has measure comparable to epsilon to m times the measure of the xr. Or in other words, what this really says, or the consequence of this, is that for any point y inside this line, okay, if the measure of this ball is positive, that means that there is a point in the support of mu inside this ball. So this says that every point y along this line is close to a point in the support of mu. So any point here, there must be a point in the support close by, within epsilon times r away. Okay, now to simplify the proof of Marstrin's rectifiability criterion in this video, what we're going to do is actually assume that our measure mu is Al4's regular. So what this means is that there's no longer the set EM. In fact, we're assuming that the whole support satisfies these inequalities. So we'll just cross this out. And what we're assuming now is that for all x in the support and all s between 0 and infinity, that these measure bounds are satisfied. Okay, so what happens then is that now these properties A and B happen for all points inside the support of mu. So in other words, whenever we have 2 points x and y in the support that are close, if we pick the alpha number small enough, then the point y must be close to the best approximating plane Lx. And then in the reverse direction, if the alpha number is small, any point on the line is close to the support of mu. So to summarize, basically the mantra that we're going to have in this video is that whenever we have, with the measure that we're considering, such that this is satisfied for all x in the support, so ignore that. So I'm using Brad-on measures such that these inequalities are satisfied. When the alpha number is small, then not only do points in the support inside this ball lie close to LXR, but also points in the line lie close to the support, which means that the support of our measure looks something like this. It's a bunch of points that are close to and distributed roughly like the line LXR. Okay, so now let's begin with the proof. So for shorthand, we're going to let alpha denote the alpha number alpha mu1, and we're going to let G denote G21, the set of multiples of one-dimensional Hausdorff measure restricted to lines to the origin. Now, for almost every x inside the supports of our measure, all the tangent measures are flat, which means that if we look at blowups at these points, txr of mu as r goes to 0, they're getting closer to the cone of flat measures, because in the limit they must be contained in the cone of flat measures. So this means that the conical distance between these blowups and the cone of flat measures must be going to 0. And recall from our discussion of alpha numbers that the alpha numbers are bounded above by this conical distance. And thus we know that at almost every point the alpha numbers are going to 0. Now let m be some large number and epsilon, so for any epsilon, we can pick a large enough number m so that if we let E be the set of points satisfying these inequalities, then this set E has positive measure. So why is that? This is kind of a typical thing in geometric measure theory. So let's let EM denote the set of X such that these inequalities hold. Now, because the alpha numbers go to 0 as r go to 0 at almost every point X, that means that for every X, eventually, alpha xr must be less than epsilon for r small enough, which means that almost every point in the support of mu is in one of these sets E sub m. And so thus, the union of the sets E sub m cover almost all of the support of mu. Now, because these E sub m's are increasing as m increases, that means that we can find m large enough so that E sub m has positive measure. Okay, so we'll let E denote this set E sub m. Now, because the alpha number is a continuous function in X, this implies that the set E is a closed set, which will be crucial for us later. By Lebesgue differentiation, there exists a point x naught in the set E and some r naught a lot less than 1 over 2m. So you shouldn't think about the precise value, but it's some number that I'm going to pick small enough to make sure everything in my proof works. Okay, so there's some number r naught less than 1 over 2 to the m's, 2m, so that if we let b naught be the ball center at x naught, radius r naught, then the complement of E in 2b naught divided by the measure of 2b naught is less than epsilon. Or in other words, E takes up all but at most epsilon percent of the ball 2b naught. Now, for technical reasons that will become apparent later, we need to have this condition for the double of b naught instead of just b naught itself. Now, let c naught be the smallest square containing b naught. So if this is our ball b naught, then the square c naught is just this right here, with sides parallel to the x and y axes. And then we're going to let E naught be the intersection of this square with E. Now, because this square C naught is a closed square and E is closed, that means that this set E naught is also going to be closed. And now a bounded set, so thus it's compact. Let's let n be some very large number and eta some very small number that we'll pick much later. So without loss of generality, by translating and rotating the support of our measure, we can assume without loss of generality that the best approximating affine measure inside the ball center x naught of radius n r naught, so in other words, inside the ball n times larger than b naught, that the support of the best approximating affine measure is the real line. For x in the support of mu and r bigger than 0, we're going to find the quantity theta of xr. And what this measures is the angle between the best approximating affine measure for mu inside this ball and the y-axis. So this will be theta of xr. Okay. Now, for points x and e naught, we're going to let rx denote the infimum over all radii r less than r naught, such that for all intermediate radii, so all radii at least r but below r naught, the angle between the best approximating affine measure in bx/ns is bigger than eta from the y-axis, and also the set E takes up all but epsilon to the 0.5% of the ball bxs. So here's a way to kind of visualize how we're choosing the number r of x. So imagine we start with a point x inside E naught, okay? And we look at the ball center x of radius r naught, okay? Now, because x comes from the set E naught, that means that x is close to the point x naught. And recall that we're assuming that the best approximating affine measure inside a much larger ball than this is equal to the real line. And because all the alpha numbers involved in this picture are small, recall that we had this lemma that said whenever you have two balls intersecting each other, or that have large intersection with each other, with small alpha numbers, then the angles between their best approximating planes is small. So that means that the best approximating affine measure inside this ball is going to have small angle with the real axis. So in particular, it has large angle away from the y-axis. All right, so basically what we do then is we start with this ball and we start shrinking it until one of these conditions is violated. Because neither of them was violated for the first ball, we look at the smaller ball. So in this picture, this line is now horizontal, so clearly it doesn't violate this one. And then we keep going down and down until we find a ball where one of these conditions is violated. So let's suppose, for example, that the line of best fit made angle at most eta from the y-axis. So then we call the radius of this ball r of x, and then we stop shrinking the ball. Okay? So why are we concerned with this value rx and where the points where the shrinking process stops? Well, it turns out that we're less concerned with the points where this shrinking stops. We're more concerned with the points where it never stops. So that is to say, we're concerned with the points where r of x is equal to 0. And for all balls, all radii bigger than 0, these two inequalities are satisfied. And the reason why is as follows. So recall that the alpha numbers for all the balls involved in this picture are small, which means, and then by our simplifying assumptions from earlier, when we were assuming that our measure mu is alpha is regular, this implies that the support of our measure lies very close to all these approximating lines. Okay, so I'm just drawing dots for the support of my measure mu. Now, since all these lines make large angle away from the y-axis, what that means is that around this point x, our measure mu actually avoids a conical neighborhood around the y-axis. And that implies that x is a cone point for the set E, at least. Well, it'll be a cone point for the measure mu, in fact. Okay, so and that will mean that the set of points where r of x is equal to 0 is rectifiable because those are all cone points for the measure mu. Okay, so and then if we show that those cone points have positive mu measure, then we'll be on track towards showing that mu is a rectifiable measure. Okay, and then this condition here, so I haven't talked much about this one yet. This is a condition mostly to ensure that the resulting set of cone points that I get in the end has large measure, and we'll see how this comes into play later. So for the points where I stopped, so where r of x is bigger than 0, I'm going to denote the stop ball by b of x, and it's going to be the ball center x of radius r of x. So recall that r of x is the infimum of radii r, so that for all radii bigger than r, these two inequalities are satisfied. But once I come down to b of x, this is the first time that one of those inequalities fails. And because these quantities are sort of continuous in the radius, that means that when these inequalities fail, we'll have equality in for one of these. So that means that the ball b of x or the radius r of x satisfies either this equation or this equation. I'm going to let stop denote the set of points x and e naught where r of x is bigger than 0. So those were places where I stopped shrinking my ball because one of the previous inequalities was violated. I'm going to let z denote the set of points x and e naught where r of x is equal to 0. So the places where I never stopped. So z, you should think of as standing for 0. And recall from the discussion on the previous slide, these are cone points for the set E. So if we can show that the mu measure of the set Z is bigger than 0, then mu gives positive measure to a rectifiable set because these are cone points and hence rectifiable. So then what I can do is an argument similar to the Besekovich decomposition theorem as follows. So what I've shown is that any measure mu satisfying the conditions of the Marstrin rectifiability criterion gives positive measure to some rectifiable set. Then I can show that if I restrict mu to the complement of this rectifiable set, that set also, almost everywhere, satisfies the condition of the Marstrin rectifiability criterion. And so it gives positive measure to a rectifiable set. And hence, using an argument very similar to the Besekovich decomposition theorem, I can then prove that actually almost all of mu is contained in a union of rectifiable sets, and hence is rectifiable. So our goal now is to show that the mu measure of this set Z is positive. Okay, so the way that we're going to show that the set Z has positive mu measure, we'll first show that it has positive Hausdorff measure, and we'll do that by showing that its orthogonal projection into the real line has positive Lebesgue measure. And the first step towards showing that is to show that the projection of the stop balls and the projection of Z contains the projection of C naught. So recall that we had this ball B naught, and C naught was the smallest square enclosing B naught. Okay? And then what we'll do later is that we'll show that the projection of this set actually has small Lebesgue measure in comparison to the projection of C naught. And that will force pi of Z to have large Lebesgue measure. Okay, so let's focus on proving this claim now. So let's suppose that we have a point y inside the projection of C naught. Okay? And suppose that we also know that y is inside the projection of E naught. Well, recall that E naught is equal to stop union Z. So that means that y is either a projection of a point in Z or a center of one of these balls, and hence y is inside the union of these two sets. So that means that without loss of generality, we're going to assume that y is not in the projection of E naught. We're going to assume that pi is in pi of C naught / E naught, as I have written here. Now, recall that we picked the set So recall that E naught is equal to C naught intersected with this set E that we constructed earlier. And E was a closed set, and this square C naught is a closed set. So that means that, in a compact set, so that means E naught is compact. So its projection is also compact. And now we have a point Y inside the complement of a compact set. Thus, if we let R denote the distance between Y and the projection of E naught, then this is a positive number. So that means that if we look at the ball, or the one-dimensional ball center at Y of radius R, so that's why I have B1 there to designate that this is a ball in the real axis, the interior of this ball is contained in the complement of pi of E naught, and its boundary contains a point in the projection of E naught. So in particular, that means that there is a point Z inside E naught that projects into this point in the boundary of B1YR. Okay, now let's look at the ball center at Z of radius R. So I claim that R is at most R of Z. Okay, because then if I prove this statement, then that implies B of ZR is contained inside the stop ball BZ. Okay, and notice that by the way that I picked the radius of the ball BZR, its projection contains the point Y. And in fact, so the projection of BZR will project down to a interval centered here of radius R. And so, but the distance between the center here and the point Y is exactly equal to R. So that will imply that Y is inside the projection of BZ and hence inside the projection of these stop balls. Okay, so thus, that's why I want to prove this claim here. And if I prove the claim, I'll be done. So let's suppose that R was bigger than R of X. Okay, so if I assume this, recall that R of X was the infimum of all radii for which these two different inequalities held. And the one that I'll be first concerned with is the one that said that theta of Z NR was bigger than eta. So what that said was that if LZNR, so if that's the best approximating affine measure, or if this is the support of the best approximating affine measure in the ball BZNR, then the angle that this makes with the y-axis is bigger than eta. So what that means is that if I look at the intersection of this line with the ball BZR, it contains a large interval inside the interior of B1YR. And by large, I mean that the length of this interval is comparable to R. So this tells me that I can find a ball centered along this line with radius comparable to R, whose projection into the real line is contained in B1YR, or contained in the interior of this ball. Okay, now recall that all the alpha numbers in my picture, for all alpha numbers of balls centered at points in E, and hence in E naught, the alpha numbers are small, which mean, and then by my simplifying assumptions about my measure, I'm assuming that my measure mu is L4's regular. And so that implies that the support of my measure, designated by red dots here, is concentrated along this line. And it's distributed along this line as well. Every point in the line is close to a point in the support of my measure. Okay, so that means that my measure mu is going to give large measure to this ball. Okay, and then recall my second property that holds for all radii r bigger than r of z. I also have that the measure of the ball center at z of radius r \e over the measure of the ball center at z of radius r is less than epsilon to the 1/2. Or in other words, the set E takes up most of the measure inside the ball BZR. And because the measure of this purple ball is large, that means that E takes up most of the measure inside this ball. And thus, that means I can find a point, let's call it W, inside the set E. Okay. Now, what I claim now is that, in fact, W is inside C naught. And then I will be done. I'll get my contradiction because if W is in C naught, then that means that W is in E intersected with C naught, which by definition is equal to which by definition is equal to E naught. Okay, but now I have a point W inside E naught that projects into a ball B1YR contained in the complement of the projection of E naught, and I get a contradiction that way. Okay, so my goal now is to show that W is inside C naught. Okay, so imagine that this figure is the previous figure zoomed out far enough so that we can see the square C naught. So suppose that this point is Z, this point is Y, and this point is W. And this circle out here, so recall that C naught is the smallest square containing the ball B naught. And so if we let this square denote NB naught, so this is the same thing as BZ naught and R naught, for N large enough, this clearly will contain the square C naught. So this blue line right here denotes the real line, which recall we're assuming is the same thing as LZ naught and R naught. So we claim that W is inside the square C naught. So why is that? So first of all, recall that Z is inside E naught. And E naught is a subset of the square C naught. So that means that if we look at this portion of our blue line here, okay, so this portion right here is pi of C naught. So because Z is in E naught, that means that the projection of Z will be in pi of C naught. And then the point Y is assumed to be inside pi of C naught. And so by convexity, if we look at the projection of W, this will be a point in between these two. And so thus, we know that W lies between these two edges of C naught. But now we have to show that it lies in between these two sides of C naught. So why isn't W some point all the way up here? Well, recall that we're assuming that the alpha numbers are uniformly small for all balls centered along the set E. And in particular, we have that alpha Z naught and R naught is at most epsilon. So this tells us that the support of our measure mu is concentrated in a small neighborhood, so this red region around the line LZ naught and R naught, or in other words, the real line. And so that means that the point W has to be inside the shaded region as well. And if epsilon is small enough, this shaded region will lie between the top and bottom edges of the square C naught. And that proves that the point W is inside the square C naught and finishes the proof of this claim. Okay, so let's recap. So we just showed that the projection of the stop balls and the projection of Z contains the projection of the square C naught. So if we can show that the Lebesgue measure of the projection of the stop balls is less than 1/2 the measure of the projection of the square, then that will imply that the Lebesgue measure of the projection of Z is positive, which will imply the Hausdorff measure of Z is positive. Now, by our assumptions about the Alfor's regularity of mu, that is to say that we were assuming that the measure of any ball centered on a support was just comparable to its radius, this condition implies that mu and Hausdorff measure are mutually absolutely continuous on the support of mu. So thus, this implies, so if the Hausdorff measure of Z is positive, that means the mu measure of Z is positive. Okay, so our goal now is to show this estimate, since by the discussion before, showing that mu Z is positive will complete the proof. So now we just focus on showing this inequality, and that will finish the proof. So what we're going to do now is show that if we pick n large enough and eta small enough, that the Lebesgue measure of the projections of these stop balls is less than 1/2 the projection of C naught. So notice that when we take the projections of the balls Bx, those are going to be balls in the real line. And so that means that we can apply the 5R covering limit to those balls. So we're going to let pi bj denote a 5R subcovering of the collection pi bx. So observe that because these balls pi bj are disjoint from each other, that means that the original balls bj will also be disjoint from each other. Okay, so now let's estimate the Lebesgue measure of the projection of the stop balls. Now, since the pi bj are a 5R subcovering, that means 5 times these balls are going to, their union will contain this set. Now, I'm calling these pi 5 bj balls, although technically they are intervals in the real line, in case that's causing any confusion. Okay, so this is at most the sum of the Lebesgue measures of the projections of 5 bj, just by subadditivity. And then each of these projections is just a interval ball whose radius is equal to 5 times the radius of bj, which means that this sum now is comparable to the sum of rxj, where we're assuming that bj is equal to the ball center at x. So we're letting xj denote the center of bj, and this will be of radius rxj. All right, so now our goal is to estimate this sum here. So what we're going to do is split the sum into two parts. Okay, so recall that for any stopped ball, there were these two equations that had to, where one of them had to hold for the stop ball. Okay, so one of them was that the measure of the stop ball minus E was equal to epsilon to the 1/2 times the measure of the stop ball. So we're going to let J1 denote the indices corresponding to stop balls of this type. Okay, so let's just estimate the sum of Rxj over these indices. By our Alfor's regularity assumption, that we're assuming that the measure of any ball is comparable to its radius, this sum is just comparable to the mu measure of the ball bj. Now we apply this equation to the terms in this sum, and we get that this is comparable to epsilon to the minus 1/2 mu bj minus E, or the sum of these terms. Okay, now recall that the pi bj are disjoint, and that implies that the original balls bj are disjoint. So that means that the sum of these measures is actually equal to the measure of the union of the bj minus E. Furthermore, these bj's are all contained inside the ball 2b0, which means that this sum is all less than epsilon to the minus 1/2 mu tb0 E. Now, recall that we picked the ball b0 using the Lebesgue differentiation theorem so that the following inequality would hold, that mu of 2b0 minus E would be less than epsilon times mu of 2b0. So substituting this inequality in for this part, we see that the epsilon and epsilon to the minus 1/2 cancel, and we just get epsilon to the 1/2 times mu of 2b0. So let me declutter things here a little bit. Okay, so we've arrived here now. Now, by Alfor's regularity, this is comparable to epsilon to the 1/2 times the radius of this ball, which is comparable to R0. And R0 is comparable to the Lebesgue measure of the projection of C0. Okay, and thus, by choosing epsilon small enough, we can make this quantity less than, let's say, 1/4 pi of C0. Okay, so now that we can make the sum over these as small as we wish with respect to pi C0, we'll now focus on the remaining indices, J2. So those are the ones where theta of xj and rj, so this is the angle that the best approximating line for nbj, the angle between that and the y-axis is exactly equal to eta. So we'll now control the sum for these indices. Okay, so this is just the text retained from the previous slide. So let's visualize what's going on so far. So let's suppose that these represent all the stop balls bx. So this is before taking the subcovering. So what we did was we looked at the projections of these balls, and we took a 5R subcovering or subcollection of the projected balls. So these will end up being disjoint from each other, and that will imply that the balls that projected onto these intervals will also be disjoint. Okay, so let's suppose that all the balls in this picture actually come from the collection J2 now. So these are all balls that project onto disjoint intervals. Okay. And they are all from the collection J2. So what that means is that if we look at the lines, so let's say this is a ball BJ with J in J2. If we look at the line LXJ, NJ, or NRJ, okay, so, actually, sorry, this should be NR of XJ, okay, so the reason why this line is a lot longer than BJ is because technically this is the best approximating line inside the ball NBJ. Okay, so I'll just erase that. Okay, so by this assumption, the angle that this line makes with the y-axis has to be equal to eta. So if eta is very small, we can guarantee that this line here is almost close to being vertical. And in fact, the projection of this line into the real line will be contained inside this interval. Okay. So now what we do is that for each one of these lines in the collection, we take a collection of disjoint balls where, so let's say for each j, we pick some balls bjk with, let's say, they are balls centered at some points xjk, and their radii is equal to, let's say, 1/10 r of xj. Okay, and they're centered along the line, so xjk, they're all inside the line lxj n rxj intersected with 1/2 or n/2 bj, let's say. Okay, and also so that if I take the sum over k of the radii, so I'll just denote the radii rjk, so that the sum of these radii is comparable to the length of these line segments, so comparable to n times r of xj. Okay, so I can get this, for example, by considering all balls centered along one of these lines of radius 1/10 r xj, and then, for example, applying the Besekovich covering to get a sub-collection of disjoint balls that still covers a large fraction of this segment. Okay, so now I have these balls. So now notice that if I look at the sum over j of r of xj, okay, now by this inequality right here, I have that this is at most 1/n times sum over j, sum over k of the r j k's. Okay, then by Alfor's regularity, this is comparable to 1/n times the sum over j, sum over k of the measure of the bjk. Okay, so that is to say, if I take the sum of the lengths of these intervals down here, that is comparable to 1/n times the sum of all these, of the measures of all these tiny balls on these line segments. Okay, but now what happens is that these balls are actually contained also inside 2b0. Okay, and so that means that the total measure here, and also moreover, these are all disjoint from each other. And the reason why is because, well, we picked the bjk. For every fixed j, the bjk's are disjoint from each other. But moreover, recall that because these lines are so close to being vertical, and because we picked the radii to be so small with respect to the balls bj, these balls along the lines actually are contained in the column above these disjoint intervals. And that forces the balls between each lines to be disjoint from each other. So, in other words, the bjk's, as we range over all j and all k, are disjoint balls. And they're all contained inside the ball 2b0. So that means that this is, at most, some constant times 1/n mu of 2b0. By Alfor's regularity, this is comparable to r0/n, and this is comparable to the measure of the projection of c0/n. But now we can just pick this number n large enough so that the sum over, so it should be over j and j2, that this sum right here we can make as small as we wish. So finally, what we've shown now is that if we take the sum over rj here, this is equal to the sum over j in, or is less than or equal to the sum over j in j1 plus the sum over j in j2. And we can make both these sums as small as we wish with respect to pi c0. So we can choose epsilon small enough and this number n large enough so that this is all less than 1/2 pi of C naught. And then retracing our steps in the previous slide, as we mentioned earlier, this is the last step in the proof that we need to verify of the Marstrin rectifiability criterion.